Hello and welcome to the course Design and Analysis of Algorithms. Today's topic is dynamic programming with an example of assembly line scheduling. An optimization problem is one that has multiple feasible solutions, each having a specific cost. Our objective is to find the best of all possible solutions. Dynamic programming is typically used to solve optimization problems. Introduced by Richard Berman in 1955, the word dynamic reflects the time-varying aspect of the problems. The word programming refers to tabular method, like linear programming to solve problem. Doesn't really refer to computer programming. Solves every sub-problem just once and save the solution in a table. Avoids recomputing the solution every time the sub-problem is encountered. It's not actually an algorithm, but a meta technique for designing algorithms. How to know if an optimization problem can be solved by applying dynamic programming? Dynamic programming works if a problem exhibits the following two properties. Optimal substructure. An optimal solution to the problem contains within it optimal solution to subproblems. Overlapping subproblems. When a recursive algorithm revisits the same problem repeatedly, then the optimization problem has overlapping subproblems. Dynamic programming, like divide and conquer method, solves problems by combining the solution to subproblems. The difference between the two is that divide and conquer algorithms have independent subproblems, while dynamic programming is applicable when the subproblems are not independent. Following are the steps to design a dynamic programming algorithm. First, characterize the structure of an optimal solution. Then recursively define the value of an optimal solution. Then compute the value of an optimal solution, typically in a bottom-up fashion. And then construct an optimal solution from the computed information. What is the drawback of a recursive algorithm like Fibonacci sequence? As we can see from the figure, that subproblems need to be solved again and again. To find the value of f of n, we need to compute f of n minus 2. Again, to find f of n minus 1, we need to compute the value of f of n minus 2 again. Similarly, f minus 3 need to be computed again, and so on. So the complexity of Fibonacci sequence is 2 to the power of n, which is very expensive. Following is the pseudocode for Fibonacci sequence using dynamic programming. What we are doing here is maintaining an array of size n and storing solution to the subproblems in that array. We use the solution of the subproblems to build the solution of larger subproblems until we can get the solution of the actual problem. For example, we are given a base case for 0 and 1. If we want to compute Fibonacci sequence of 2, we can use the result stored in the 0th and the first index. Once we compute the value of Fibonacci sequence of 2, we store it in the second index. So in the future, when we need to calculate the value of f3, 4 and 5 and so on, we can use the stored values to build the solution for the larger numbers until we reach the final solution. So what is going to be the complexity of this algorithm? Since we have a single for loop here, so the complexity of this algorithm becomes linear, big O of n. Note that when we were using the recursive algorithm, the complexity was 2 to the power of n, which has been reduced to big O of n when we are using dynamic programming. To see how dynamic programming works, let's look at this example of assembly line scheduling problem. We first define the problem and then we build the solution to the problem using dynamic programming. An automobile factory has 2 assembly lines. Each line has n station from S1 to Sn. The first number here represents the line number and the second number here represents the station number. So S13 will be station 3 of line 1. Corresponding stations S1J and S2J perform the same function but can take different amount of time, A1J and A2J. So station 2 on both lines are doing the same work but can take different amount of time. Entry times and exit times of those lines are defined as E1 and E2 for line 1 and line 2 and X1 and X2 for line 1 and line 2 respectively. After going through a station, a car can either stay on the same line at no cost or transfer to the other line with some transfer cost. We want to know what station should be chosen from line 1 and line 2 in order to minimize the total time through the factory for one car. A brute force solution to this problem is to enumerate all possibilities of selecting stations and compute how long it takes in each case and choose the best one. So there are n stations, and for each station either the fastest way can be through line 1 or line 2. Here line 2 is represented by a 0. So for n numbers we have a possibility of a 1 or a 0. So there are 2 to the power of n possible ways to choose stations. This becomes infeasible when n is large. The first step into designing an algorithm using dynamic programming is to define the structure of the optimal solution. How do we compute the minimum time of going through a station? Let's consider all possible ways to get from a starting point to some station J on line 1. We have two choices here. Either we can come from the same line with no additional cost, or we can come from the other line with some transfer cost. Suppose the fastest way through the station was through the previous station on the same line. So we must have taken a fastest way from entry point through to the previous station. If there were a faster way through this station, we would have used it instead. Same is the case with the previous station on the other line. So this problem exhibits optimal substructure property. An optimal solution to a problem contains within it optimal solution to subproblems. This is the optimal substructure property. So we use this property to construct an optimal solution to a problem from optimal solutions to subproblems. The second step to design an algorithm using dynamic programming is to recursively define the value of an optimal solution. So we define the value of an optimal solution in terms of the optimal solution to subproblems. Our strategy is to build a table to save previous results so that they don't have to be computed or recomputed each time. Here we define some variables and tables. F star is the fastest time to get through the entire factory. F I of j is the fastest time to get from the starting point to station Sij. L star is the line number which is used to exit the factory from the nth station, and Li of j is the line number, either 1 or 2, whose station was used to reach station j on line I. Our objective function is the f star, which is the minimum of the two values. Either we exit from line 1, so the fastest time to station n on line 1 plus the exit time on line 1, or the fastest time to station n on line 2 plus the exit time on line 2. The base case in our case will be station 1 on both lines. So the cost of finish time of station 1 on line 1 and 2 will be the entry time to a line plus the time taken, which is the assembly time of a particular station. And in general case, from J to N, the fastest way to a station on line 1 is either from the same line of the previous station or from the previous station of the other line plus some transfer cost. So F1 of J will be the minimum of the two costs from either this line or this line. Finish time of the previous station on the same line plus the assembly time plus finish time of the previous station on the other line plus the transfer cost and plus the assembly time on this particular station. So we will choose the minimum values of the two, which will be the fastest time to reach this station from the start or starting point. In summary, to fill the F table, which stores the finish time to all stations, for station 1, we will use entry time plus the assembly time of that station. And for the remaining stations, we will use the minimum of the cost coming from the previous station on the same line plus the assembly time of that station, or the finish time of the previous station in the different line plus the transfer cost plus the assembly line of this station. Once we have defined the value of optimal solution, we can compute the optimal solution using the bottom-up approach. We first find optimal solution to subproblems and then use them to find an optimal solution to the problem. For j greater than 2, each value of Fij depends only on values of F1j minus 1 and F2j minus 1. So idea is to compute the value of Fij as follows. In increasing order of j, to start off with, we will find the value of F1 of 1 and F2 of 1. Once we have found the fastest way to station 1s on line 1 and 2, we can use them to find the value of fastest time to station 2 on both lines. Here, to compute the value of the fastest time to station 2 on line 1, we only need the value of F1 of 1 and F2 of 1. Similarly, to find the value of F1 of 5, we have already computed the value of F1 of 4 and F2 of 4. So to compute this value, we only need these two numbers. We do not need to go back again here because all these values have been computed and stored. Let's solve the following example of assembly line scheduling to see how the process works. We are maintaining an additional L table which keeps tracks of which lines were used to fastest reach a particular station. We will need this table at the end to figure out the fastest path through the assembly line. So what will be the fastest time to station 1 on line 1? 2 for the entry plus 7 for the assembly, total of 9. So we reached the fastest time to reach this station is 9 through line 1. So we enter 1 in the L table. For station 1 line 2, 4 is the entry time plus 8 is the assembly time, a total of 12. So we enter 12 and it entered through line 2. So in the L table we will write 2. For station 2 line 1, what will be the fastest time to reach here? There are two possible ways, one from line 1 and one from line 2. So if we come from line 1, the fastest time to this station was 9. So 9 plus 9 is 18. And if we come through this station here, the fastest time until here was 12 plus the 2 transfer cost, which is 14, plus the 9, which is 23. So 18 is smaller than 23. So we will get the fastest time through line 1 of 18. So if we will write 18, and in the L table we will write 1. For station 2, line 2, we do the similar process. The fastest time to station 1, line 1 was 9, plus the 2 is 11, and plus 5 is 16. From here it is fastest time was 12 plus 5, it is 17. So the minimum value is 16 from line 1. So we enter 1 in the L table. And we repeat the similar process to fill up the tables. So the fastest time to station 3, line 1 will be 20 from station 2. Fastest time to station 3 on line 2 will be 22 from station 2. The fastest time to station 4 on line 1 will be 24 from line 1. The fastest time to station 4 on line 2 will be 25 from line 1. On station 5, if we want to compute the fastest time, it's going to be 24 plus 8, which is 32. And from this station, it's going to be 25 plus 2 is 27 plus 8 is 35. So the fastest time is 32 from line 1. Similarly, station 5, line 2, the fastest time is 30 using line 2. And on station 6, line 1, the fastest time is 35 from line 2. And station 6, line 2, the fastest time to reach there is 37 from line 2. The time to exit from line 1 will be 35, which is the time here, plus 3, which is 38. And the fastest time to exit from line 2 will be 37 plus 2, which is 39. So our F star will be the minimum of 38 and 39, which is 38, which we got from line 1. So our L star will be 1. So for this problem, the fastest way out is 38, and from the last station we are using line 1 to exit the assembly line. Following is the pseudocode for assembly line scheduling problem to find the fastest way through the assembly line. Initially, we will compute the fastest time to station 1 on both lines, and using these values we will compute the fastest time from station 2 to station N for both lines, and in the process we will fill up the F table and the L table. Then we compute the value of the fastest time through the entire factory by adding the fastest time to the last station in the line plus the exit time. So what will be the complexity of this algorithm? Since we are using a single for loop, the complexity of this algorithm will be big O of n. Recall that when we use brute force, the complexity for this problem was 2 to the power of n, which has been reduced to big O of n. The last step into designing algorithm using dynamic programming is to construct an optimal solution once we have computed the optimal solution. And the L table will help us in identifying the fastest way through the assembly line. From the value of L star, we will backtrack into the table to figure out the fastest path. Since the L star is 1, we know that we came or we exited the assembly line from station 6 from line 1. So we go to the index of line 1 station 6. So we came to line 1 station 6 from line 2. So we go to station 5 line 2. Since from this station we went to this station, that's why we have a 2 here. So on station 5 line 2, we came here from line 2 station 4. So we go to the fourth index of the second line. On line 2 station 4, we reached here from line 1. So for the third station we move to line 1. And we came to station 3 on line 1 from line 2 or from station 2. So we backtrack to station 2 line 2. And we came to station 2 from line 2 from line 1. So we go to line 1 station 1, and station 1 line 1 we came from line 1. So we will just draw an arrow here, and using this information we can trace the path which is the fastest way through the assembly line. So if you add up all this cost in the red path, that will be 38, which is the fastest time to exit the assembly line. In today's lecture, we learned how to design an algorithm using dynamic programming and applied that into designing the solution to the assembly line problem. I hope you have enjoyed today's lecture. Thank you and have a nice day.